Today you were assigned 6 problems from page 446, so this is part of the chapter review for the section. Specifically, we're reviewing for the quiz on 7.4 and 7.5, so I assigned you 3 problems from 7.4 and 3 problems from 7.5. So I'm going to do one from each, even though if you need additional help, you can refer to the videos that deal specifically with these sections. From 7.4 I'll do problem number 15, and from 7.5 I'll do problem number 18, leaving 13, 14, 16, and 17 for you to do. So I will start with number 15, which is out of 7.4. So we have 5x equals to 3y minus 2 and 3x plus 2y equals to 14. It says solve the linear system using elimination. If you remember, 7.4 was all about modifying systems so elimination could be used. So looking at this problem, first of all, my x's and my y's are not aligned. I have on the bottom the x and y on one side, on the top I have the x and the y on different sides. So what I'm going to do, I'm going to rewrite the top problem right over here, and then I'm going to make it so both the x and y are on both sides. So I'm going to move the y to the left. I could move the x to the right as well, but I'm trying to match the top one so it looks like the bottom one. So I'm going to subtract 3y from both sides. Once I do that, I get 5x minus 3y equals to negative 2. Now I'm just going to rewrite this problem back here underneath the original second equation, since the order doesn't really matter. Now that they're aligned, I can look and see how I can deal with this problem in terms of elimination. I'm looking at the coefficients for x, 3 and 5. The GCF is 15. I'm looking at the coefficients for the y, it's 2 and 3 with the GCF being 6. So no matter what I do, I will need to modify both. None of the GCFs are already present in the coefficients. So this is one of the more difficult cases where no matter which coefficient for whichever variable you try to modify, you'll need to modify both equations. I think modifying for the y is easier because getting up to a 6 for both is going to require a little less work than getting up to 15 for both of the ones for x. So I'm going to multiply the top equation by a 3, because 3 times 2 will give us a 6, and the bottom one by a 2, because 2 times negative, or 2 times 3 is going to give us a 6 regardless of the signs. So 3 times 3x, that's 9x. I'm just going to write them down here. 3 times 2y, 6y. 3 times 14, that is going to be 42, if my math is correct. 2 times 5x, that's 10x. 2 times negative 3, that's negative 6y, equals to 2 times negative 2, negative 4. And now I have the same coefficients for the y's, and it allows me to eliminate them. I'm going to use addition. So if I add these two, they will cancel each other out. So 9x plus 10x, that is 19x. 6y plus a negative 6y, that's 0. And 42 plus a negative 4, that's going to give us a positive 38. So essentially 19x equals to 38. If I divide both sides by 19, I should get x being equaled to a 2. So now that I have my x, I can very easily find y. All I need to do is plug in the x, the value of the x, back in to the original equations, either over here or over here, and solve. I'm going to choose the top one. So 5 times 2 equals to 3y minus 2. So 10 equals to 3y minus 2. Add 2 to both sides. 3y equals to 12. Divide both sides by 3. y equals to a 4, and my order pair is 2 because x goes first, 4. So that was number 15. By elimination, I had to modify them first to make them aligned. So the x and the y were both on the same side of the equation. Then I modified both equations because I had to. A single modification would not have been enough, and I chose to modify the coefficients of the y, made them both into 6's. Obviously the entire equation changed as well. I did my elimination, and then I plugged in the value of x in to the first original equation, and I got my y. Moving on to number 18. In here they're asking us to figure out if it's a one solution, no solution, or infinitely many solutions type of a problem, and explain. Good, I like explaining. Just like before, there's many ways you can solve this particular problem, but elimination just seems to be the get-go or the easiest way of doing it. So, but before I can eliminate them, I have the x and the y, just like in the previous example, on different sides here, and they're on the same side over here. So I'm going to change the top equation. So I'm going to rewrite it right over here, so that both x and y are on both sides, and I can do that by subtracting 2y from both sides on the top equation. That gives me 4x minus 2y equals to 6. So all I did is just on the top equation I subtracted 2y from both sides. I'm going to rewrite it back underneath that second equation because the order doesn't really matter. Now I'm going to take a look at these two. I can eliminate now, not a problem. And I would use addition. 4x plus 4x, 8x. Positive 2y plus a negative 2y, 0. And 10 plus 6, 16. So 8x equals to 16. Divide both sides by 8. X equals to a 2. Now right away I know this is a one solution problem, because if this was a no solution problem, I would have something like maybe 0 equal to 2 or 4 equal to 8. Something that cannot be equal to each other, a different thing on both sides of the equations. If it was an infinitely many solutions problem, I would have probably 2 equals to 2, or 0 equals to 0, or 5 equals to 5. So right away I know this is not a case of where it's no solution or infinitely many solutions. This is a one solution problem, and to double check that, I can plug that x value in right over there at the very top and find my y, and that way I'll have a single point of intersection. So 4, 2 equals to 2y plus 6, 8 equals to 2y plus 6, subtract 6 from both sides, 2y equals to 2, divide both sides by 2, y equals to 1. So the answer is 2, 1, x goes first, y goes second. It's a single point of intersection. There's only one solution to this problem. So this is not a no solution, and this is not an infinitely many solutions type of problem. This is a one solution type of problem. And you can figure that out right at the end of the elimination, because you get either x equals to something if you chose to eliminate y, or y equals to something if you chose to eliminate the x. If you get a case where, for example, it was 2 equals to a 2, for example, that would be an infinitely many solutions. If you had something that looked like 0 not equal to a 2, that would be a no solutions type of problem, but that's not what we got. We got x equals to a 2, and we could plug that in and get our y. So this was a one solution type problem. So thank you very much, and I'll see you guys tomorrow.